All right, so we have been talking in class about how things move, basically, velocity and acceleration. And that is an area of physics called kinematics. What we need to get into now is why do things move? Why do they accelerate? And that sort of thing. So that's an area called dynamics, and it has to do with Newton's laws of motion. So that's what we're talking about today is Newton's laws of motion. And basically the reason why things accelerate is because a force acts on them. So a force is any push or pull that acts on an object. Scientists have broken forces down into 4 different categories. There is gravitational force, which is an attractive force that exists between all objects. So there is an attractive force between you and every other object around you. Again, we kind of talked about gravity already. Gravity has to do with the masses of the 2 objects and how far apart they are. So the gravitational force that exists between you and whatever's around you is based on your mass, the other object's mass, and how far apart you are. So why don't we feel those gravitational forces? It's because the gravitational force that's between you and the Earth is so much larger because the Earth has an extremely large mass. So the gravitational force between you and the Earth is so much larger that you don't feel the other gravitational forces that exist between you and the other objects around you. Another type of force is called an electromagnetic force. This results from electrically charged particles. And this is actually probably most of the forces that you encounter are electromagnetic forces. These are the forces that make tape sticky and that sort of thing. There's a strong nuclear force. That's the force that holds the particles of a nucleus together. If you think about it, the nucleus of an electron, or excuse me, the nucleus of an atom has a bunch of protons and neutrons in there. Well, the protons are positively charged. The neutrons have no charge. And typically, things that have the same kind of charge will want to get as far away from each other as possible. So those protons that are in there would want to repel each other. So there needs to be a very strong force that holds those particles in there together. So that's the strong nuclear force. And then just what they call weak force, because it's the weakest of all these types of forces. It's a type of force that can result from certain types of radioactive decay. Really nothing for us to be concerned with. In fact, there's nothing that we do really with these 4 different categories of forces. We just want to talk about the fact that they're out there. I just lost my controls up there, so bear with me while I find them again. All right, I got them back. And there they went again. Not sure what's going on with this thing today. Okay, let's see if we can get them to stick around this time. So, getting into Newton's laws. Newton's first law of motion is also known as the law of inertia. As you might know from the Bill Nye the Science Guy theme song, inertia is a property of matter. Inertia is an object's tendency to resist a change in its state of motion. Things that are sitting still want to remain sitting still. Things that are moving want to keep moving in a straight line at a constant speed. That's what inertia is, the tendency to change or to resist a change in that state of motion. An object's state of motion can be changed when a force acts on it. Not just any force. You can push on a wall, that applies a force to the wall, but the wall isn't going to change its state of motion. There has to be a net, what's called a net force. So in the absence of force, there's not going to be any change in state of motion. Newton's first law says that an object with no net force acting on it remains at rest or moves with constant velocity in a straight line. You may have heard it stated as objects at rest will remain at rest, objects in motion will remain in motion unless they are acted on by a net external force. There's always more than one force acting on an object. Net force means that some of the forces are larger than the others, and so there's a total amount of force acting in a certain direction on the object. And that will cause it to move, accelerate. And there went all my controls again. This thing's being really goofy today. I'm just going to roll with it. So Newton's second law of motion says that a change in the state of motion is an acceleration. Well, that's not his second law, but that's what we're talking about. Any change in a state of motion is called an acceleration. It either changes speed or it changes direction. We talked about acceleration, well, velocity is both speed and direction, and any change in velocity, either change in speed or change in direction, is an acceleration. So any change in motion is an acceleration. And acceleration depends on how much force is applied, net force is applied to the object, and how much mass that object has. Now, you guys have probably experienced this firsthand. You push on an empty shopping cart, and it'll move fairly easily. You get that shopping cart loaded down with stuff, so there's more mass to it. It's the same shopping cart sitting on the same floor, but now it's got a lot more mass, and you push on it with the same amount of force, and it doesn't move as easily. Okay? So acceleration, how well you can get an object to change its state of motion, will depend on the amount of force that you apply to the object and how much mass the object has. So Newton's second law, Newton figured out this relationship, and it became his second law of motion. It says that the acceleration of an object varies directly with net force. That means the more force you apply to an object, the more it's going to accelerate. And inversely with the object's mass, which means that if you apply the same amount of force to an object that has more mass, it's not going to accelerate as much. So mathematically, what that looks like is acceleration is equal to net force divided by mass. This is the Greek letter sigma, which stands for the sum of all forces. Really, this is technically what the equation looks like. We're not going to see this in any of the equations that we're writing down. It'll just look like F equals ma. Remember, physicists don't really like leaving fractions in their equations if they can help it. So Newton figured out that acceleration is equal to net force divided by mass. They rearranged the equation to show force is equal to mass times acceleration. It is important to note, even though we don't write it down when we write down this equation, but it's important to remember that this force is net force. Sometimes we'll write it F net, because we're going to have more than one type of force. And again, when we have more than one type of the same thing, we will show which one we're talking about by using subscript letters. Objects will always accelerate in the same direction as the net force. So if the net amount of force acting on an object is to the right, it's going to accelerate to the right. Show you what I'm talking about. If you're pushing on something, say that shopping cart I was talking about, pretty good looking shopping cart right there. That force that you push with, we call that the applied force, FA. Well, between the wheels of the shopping cart and the floor, there's always some amount of friction. And that acts in the opposite direction to the motion. We call that FF, force of friction. As long as the applied force is bigger than the friction force, you're going to have a net force. So if I draw those arrows over down here, FA and FF. Sorry this is so boring, but my controls keep disappearing, so I can't change the pen colors or nothing. This right here would be the net force acting on the shopping cart. And since that is pointing in this direction to the right, that shopping cart is going to accelerate to the right. So objects will always accelerate in the same direction as the net force that's being applied to them. And since Newton did all this work in the area of forces, they have named the unit of force after him. So force is measured in a unit called newtons. If we look at it carefully, it's mass times acceleration. So it's 1 newton is a kilogram of mass times a meter per second squared of acceleration. So it's 1 kilogram of mass being accelerated at 1 meter per second squared would require 1 newton of force. Newton's third law of motion, you guys commonly know it as the action-reaction law. For every action, there's an equal and opposite reaction. That's because forces exist in what we call action-reaction pairs. So when you apply a force to an object, you'll feel that same amount of force because the object applies it back on you. When you push that shopping cart, you can feel a force pushing back against your hands. When you apply a force to make a ball stop, when you catch it, you can feel the force back on your hands. You can feel your hands catching that ball. Okay? So Newton's third law says that when one object exerts a force on a second object, the second object exerts a force back on the first object that's equal in magnitude and opposite in direction. You push forward on a cart, the cart pushes backward on you with the same amount of force. So again, these forces always exist in pairs. They're called action-reaction pairs. So when you do something like lift an object, the object will exert a force on you equal and opposite to the amount of force you're exerting on an object. So why does the object go up? You would think that that would create a situation where there's no net force, and therefore it wouldn't move. What you have to remember is that gravity is also exerting a force on the object. And so if your force is greater than the force due to gravity, gravity's pulling downward, you're pulling upward, then the object is going to move upward. Okay, kind of like the shopping cart thing. If you're pushing on a shopping cart, it's pushing back on you with the same amount of force. So why is it moving? Well, it's because the force that you're pushing forward with is greater than the force of friction that exists between the cart and the floor, just like we drew back here. So you do create a net force on the object, and that gets the object to move. Looking more closely at these action-reaction pairs, What we're talking about is, let's say you go to pick up a bowling ball. Okay? When you lift upward on the ball, that's your force applied. Yes, the ball exerts the same amount of force back downward on your hand. The force of the ball. Okay? And gravity is pulling downward on the ball. We call that Fg, the force due to gravity. Interestingly enough, the ball is also pulling upward on the earth with the same amount of force. Force on the earth, we'll call that Fe. Okay? I need to have my controls back because I need to get rid of some of these lines. See if this brings them back. All right, we're in business. So, why does the ball move? Well, when we're looking at the forces on an object or the motion of an object, we only consider the forces that are acting on that object. We don't consider the reaction pairs. So, the force that the ball applies on your hand, we ignore. The force that the ball applies on the earth, we ignore. And as I said, as long as you pull upward with a force that's greater than the force gravity is pulling downward with, there will be a net force upward, and the ball will accelerate upward. You can lift an object up with no acceleration if you apply a force that's equal to the amount of gravity. All you have to do is equal the force due to gravity, and you can pull something upward with a constant velocity. All right, so that is Newton's 3 laws of motion, and we will discuss in class some example problems and whatnot. Sorry the video was a little bit longer, but that's because of the issues I was having with the smart recorder. All right, we'll see you.